All right. Our next talk is by Professor Adi Ben Israel. I grew up on Ben Israel and Greville's book on generalized inverses of matrices. And Adi was a good friend of mine too. And he also wrote, I want like to do a little bit of publicity of my own work a little bit. Adi also wrote the foreword for my book on generalized inverses over commutative rings. And of course, as I said, I grew up on his book, and of course, also C.R. Rao and S.K. Mitra book on generalized inverses. It's a great pleasure for me to introduce Professor Ben Israel, and he will be talking on matrix volume and its applications. Adi, start, please.
My lecture, Matrix Volume and Application, is dedicated to our great teacher, Professor Rao, on his 100th birthday. I wish Professor Rao many more years of good health and good statistics. The volume of an M by N matrix of rank R is defined as the square root of the sum of squares of the determinant of its maximal non-singular submatrices, and 0 if the matrix is 0. Equivalently, the volume of the matrix A is the product of its positive singular values. Definition 1 applies also to non-numerical matrices such as Jacobian. Y volume, every unit cube in the range of A transpose is mapped by A into parallelopiped in the range of A of volume vol A. Similarly, every ball of volume 1 in range of A transpose is mapped into an ellipsoid of volume vol A. So every volume that can be approximated by cubes or rectangles or whatever boxes, therefore is mapped by A into a volume which is the original volume times the volume of A. Special cases, if we have a non-singular matrix W, the volume of the parallel pipe spanned by its columns is the determinant of W. It is a signed volume because the determinant can be positive or negative. The volume of W is the absolute value of the determinant. If the matrix is of full column rank, then the same parallel pipe, the volume is given by the Gram determinant, and the volume of W is equal to the square root of the determinant W transpose W. Now, if a matrix is square, the determinant can be 0, but the volume can be still positive. For example, if you take the 2 by 2 matrix of ones, the determinant, of course, is 0, but the volume is 2, the square root of 4. And in fact, the unit cube in the case of this matrix is just the range of A transpose is just a line, and the unit cube is the unit vector on that line, and it is mapped into a vector twice the length. The minimal norm least square solution, which is the Moore-Penrose inverse of A times the vector the right-hand side B, is a convex combination of the basic solutions. The basic solutions are when you restrict the equation Ax equal B into the maximal non-singular submatrices and the corresponding portion of the right-hand side. The convex weights of this combination are proportional to the determinant square of Aij of a maximal non-singular submatrix. And because the sum of them is just the volume square, this is the weight. And the corresponding result for the Moore-Penrose inverse is that the Moore-Penrose inverse is a convex combination with the same weights of the inverses of the basic matrices, that is non-singular, maximal non-singular submatrices, padded with enough zero to make this compatible. A full rank factorization of A is CR, where C is the full column rank and R is of full row rank. Example, singular value decomposition, QR, etc. And we have an interesting result that the volume of A is equal to the product of the volume of its factors. So it's the volume of C times the volume of R. This follows directly from definition 1, and in fact, we can use this to prove the equivalence of the two definitions. Both the volume and determinant are best understood in a setting of multilinear algebra. So let V be a finite dimensional linear space over a field F. The exterior or wedge product is an operation from V times V to V that is anti-commutative. The scalar comes out and it is distributed in both variables. Now the case exterior power of V, denoted wedge KV, is simply the space of all exterior products of K elements from V, and in particular the dimension of wedge K Rn is n choose K. The compound matrix comes next. It is the matrix representing the linear transformation from the K exterior product of V to the K exterior product of U, and it is defined by CKA, the linear transformation represented by that matrix, times the exterior product of X1 to XK, equal to the exterior product of AX1 to AXK. So the compound matrix is CKA is M choose K by N choose K, and it is of rank RK, R choose K, and in particular CRA is of rank 1. Now, if A is N by N, then CNA is just the determinant of A, as we can see in this relation that the exterior product of AX1 to AXN is the determinant of A times X1 to Xn. And this is for all n vectors in Rn. If the matrix is m by n of rank R, then the absolute value of CRA is the volume of A. And the same relation for any R vectors has plus minus vol A in front. The compound matrix allows us to define some intermediate volume. So the K volume will be just the Frobenius norm of CKA, or equivalent in terms of singular values, it is square root of the K symmetric function of the square of the singular values. And these have also interesting volume interpretation, but they are beyond this lecture. Let's look now at the singular value decomposition of A. I write it in minimal form so that 0 singular values will be deleted together with the corresponding columns of U and V. So in particular, U and V are not unitary matrices, but just the columns that correspond to the positive singular values. The columns of U are orthonormal bases of the range of A, etc. The corresponding singular value decomposition for CRA, A is of rank R, is this. The metric CRA, sigma, the metric sigma comes out as the volume of A, a number. The vectors U, the matrices U and V come out as U wedge, V wedge, and these are the exterior products of the columns of the matrices, and there are also the Grassmann or Grassmann-Plücker coordinates of the range of A and the range of A transpose. And now move to the differential geometry of surfaces. This stuff is 200 years old by Gauss, given by Gauss. On the left, we have a part of the XY plane. On the right, we have a part of a surface obtained by mapping XY plane into the surface by the mapping phi. And we define three objects, E, F, and G. E is the dot product of the X gradient of phi with itself. G is same for the gradient phi y, and F is the mixed dot product. The first fundamental form of Gauss is the length element, ds, and in fact, ds squared is a quadratic in dx and dy, with E, 2F, GS coefficients. But we are interested here in the area element, dA, and we can write it, we can simplify it as the square root of EG minus F squared dx dy. And in particular, the area of phi u for any set u on the left is the integral over u of the square root of EG minus F squared dx dy. And this is due to Gauss. And the connection with the previous, with the present lecture is that the square root EG minus F squared is the volume of the Jacobian J phi in the background. And to show this, keep the same picture and consider the mapping phi that takes xy into xy and z, which is itself a function small f of xy. The Jacobian is 3 by 2, and there it is, and its columns are phi x and phi y before. EG minus F squared, if you do the arithmetic, is 1 plus fx squared plus fy squared, and it is just the volume square of the Jacobian using our definition. So we can write dA as the volume of J phi dx dy. So this is for the area element dA, and in general, the area of phi u on the right is an integral over u in the left of that volume times dx dy. So this is the preparation for the change of variable formula in integration. The unit normal at the surface must be perpendicular to phi x and to phi y, and therefore it must be proportional to minus fx, minus fy, and 1. But it is normal, it is unit vector, so we have to divide by the Euclidean norm, and it is just the volume of the Jacobian. So this is the formula for the unit normal, and we get the same formula for an n-dimensional surface. And now we move to change of variables integration. The formula given by Jacobi in 1840. We have an integral over the set phi u of a function capital F. Okay, and instead we sometimes prefer to do the integral over u of a more complicated expression, but it may be actually a simpler integration. So on the right you see the composition of capital F and phi, and the absolute value of the determinant of the Jacobian. Now, if u and phi u are in spaces of different dimensions, then we cannot use A because the Jacobian is not square. However, if the Jacobian is a full column rank throughout U, then we can replace the absolute value of the determinant by the volume and get this formula, which is the change of variables formula for integration between spaces of different dimensions. In particular, if m is equal to n, and I should add that the Jacobian is non-singular, then the volume is just the absolute value of the determinant, and B reduces to A. Okay, here is an illustration. I have to integrate a function capital F on the surface S, and in particular on a portion phi u. And this integral is the same as the integral over u below of the function. And now the function does not mention z. Instead of z, we have fxy. And we have the volume of the Jacobian is 1 plus fx squared, square root of 1 plus fx squared plus fy squared. When we have a vector field and we want to integrate it over the surface S, the same formula gives us integral over S of f ds, and on the right you have the integral over u, and here we have the inner product of f and the unit normal to the surface times the volume of the Jacobian times dx dy. And here is a magic trick. The volume is the square root of 1 plus fx squared plus fy squared. The unit normal has the same square root in its denominator, so we get a wonderful cancellation, and the integral of f ds over s is the integral over u of a simpler expression, and the square root disappeared. Application to probability. Let x1 to xn be random variables with a joint density f of x, fx, h from Rn to R, a well-behaved function. In particular, it must depend on some of the variables. So we assume that dh, dxn, the partial of h with respect to xn, one of the variables, call it xn, is not 0. And it is required to find the density of the random variable y, which is h of x1 to xn. So we solve for the variable xn in terms of y, and we call this h inverse. So xn is h inverse of y given all the other x's. Change variables from x1 xn to x1 xn minus 1 y, so we still have n variables, and calculate the determinant of the Jacobian, and it is the partial of h inverse with respect to y. The Jacobian has the first n minus 1 rows, the same as the identity matrix. So the determinant is just the bottom right element, which is partial of h inverse dy. And we can write the density of y using the Jacobi formula. So it is the integral over the variables x1 to xn minus 1. And we have the determinant of the Jacobian. Alternatively, we can structure our variables differently. We can say that x1 to xn will be phi of x1 to xn minus 1, and the function phi is x1 to xn minus 1, followed by xn, which is h inverse of y x1 xn minus 1. Then the surface integral of the density of x over vy is the surface where the random variable y gets the value small y. So the integral of fx over that surface is then, using the volume expression, the integral of fx, the density of x, times the volume of the Jacobian, times dx1 dxn minus 1. And here we have a nice result that if the ratio of the two scales we used, one of them was the partial of h inverse with respect to y, and the other one was the volume of the Jacobian. So if the ratio of these two does not depend on the axis, may depend on y, but not on the axis, then the density of y is that expression, a, comes out of the integral because it does not depend on x, times, and now we have a much simpler expression, the integral of the density of x over the set vy. This is where the random variable y has the value small y. Now, why would this condition be satisfied? Well, it is satisfied for some very useful functions. For example, the linear combination of the variables, the linear combination of the x's, sum of x squared, or the exponential of the sum of the xi's. So for these three functions, perhaps others, we can get very simple expressions for the density of the function of the random variables. Check the condition for the function for the sum of squares. So when y is sum xi squared, we can solve for xn as plus or minus square root of y minus the sum of squares of all the others. And then the partial of this with respect to y is simply plus or minus 1 over 2 the square root. Similarly, the volume of the other Jacobian will be square root of 1 plus the sum of squares of the partial of h inverse with respect to xi. And when we simplify, we get square root of y divided by the same square root. And therefore, the partial of h inverse with respect to y divided by this is simply 1 over 2 square root y. It is independent of the xi's, and therefore the density of sum xi squared is expressed in terms of the integral of the density of f with respect to x on the sphere of radius square root of y, because on that sphere the sum of xi squared is equal to y. Okay, this correlates this result, and now let's look at a strange example. I calculate here y is the sum of square of two independent, identically distributed random variables uniform in 0, 1. And here is what the density looks like. It is constant from 0 to 1. And it is, after this, it goes down according to minus arc cosine of 1 over square root y. So it is pi over 4 from 0 to 1. So if we have a conditional density, that is, I add the condition that the value of y must be less than or equal to 1, I get a uniform distribution from 0 to 1, which is very strange. Before I explain this geometrically, my good friend Yishai Weissman from the Technion was moved by this example to calculate this density of y for all n. And in fact, this is the only one that is pathological in this sense. And here is a geometric explanation using the formula. What we do is that we calculate the length of this arc, of this quarter of a circle, and divide by 2. This is by over 4. So when y is less than 1, we get the full quarter circle. But when y is greater than 1, then we only get part of the quarter circle, and this is the part that appears in the formula pi over 4 minus the arc cosine. Okay, now since the volume was first announced, there are many applications. One is for face recognition, where we have an atlas or album of faces, and we have a new face, and we ask, is it included in the album? And the answer is yes, if the volume of the difference between the new face and one of the faces in the album is less than epsilon, where epsilon is fixed, and not otherwise. And in fact, this method was checked, compared with 4 other methods, and it is better when you have little information. So this expresses the green The accuracy is replaced by the green line. There are other applications, and I listed here some of them. I also have a bibliography that consists of 100 plus items, some with PDF links and other links. And if you are interested, please let me know and I'll send you the full slides of this lecture with the bibliography and some other stuff I could not cover in the allotted time. Thank you for your attention.
Thank you, Professor Ben Israel. It's nice to see you, of course.
Yeah, he is as young as he was.
Yeah,
No change.
It's very nice to see you. And if I remember correctly, at one time, Dr. Prasad and myself, we were also looking at exterior products and of course compound matrices. Okay, but the volume itself is an interesting talk. And I also remember attending one of your talks about the face recognition, which was very interesting as an application of this. But I'm sure those who are interested can write to you. We are running out of time a little bit. If it is okay with you, we thank you for your talk. Okay, and